maybe give you, as I'm doing these problems, I'm going to do them like I would do them. So I'm going to do them fairly quickly. You can watch this video after class if you want. Effective rate, that's the effective yield. Look for these keywords. Go back to the formula sheet in the back of the test and look for something that says effective annual yield. And you can either use the formula or you can use the calculator function. And this says round to the nearest hundredth of a percent. So your answer should be written as something percent, corresponding to a nominal rate of 6.92%. So this is what you'd want to enter in if you use the calculator function. If you use the formula, you have to convert this percentage to a decimal. And that's the general rule for all of these formulas that we worked with for the rate. Decimal for the rate, I% for the TVM solver, the calculator. Yeah, and so you just plug in the value of R. By the way, it says compounded quarterly. So the little m value, or it might be n, is equal to 4. But whatever it is, it appears twice in the formula. So if we use the formula, it's going to be this. If you remember what I said about this particular problem like this, is we're looking for an effective rate, and the effective rate will be just a little bit larger than 6.92. So it might be 6.97, or it might be 7.05 or something like that, but it's going to be very, very close to this, the effective annual yield. So we're going to get the calculator out and just type this in exactly as it appears. 1 plus 0.0692 divided by 4. Okay, so this is going to evaluate what's in parentheses, and then I have to take it to the 4th power. I get this, and then I have to subtract the 1. All right, so this works out to be 0.0710165,404. If you convert it then to a percent and move the decimal point over 2 places, it's 7.10165,404%. And then here it says round to the nearest hundredth of a percent. So here is the hundredths place on the percent. So we want to round there. Peek at the next digit. It's 4 less, so we round down. So 7.10%. And round and list your answer as a percent, rounded to the nearest hundredth of a percent. Notice this number is a little bit larger than 6.92, which will always be the case. Okay, so Wesley says graphing stuff. Okay, so we'll maybe shift back here to the graphing problems. You can expect to see one of every kind of, not one of every kind, but you know, a good selection of problems from each of the section. In this one, I think there's just 1 page of problems. In the other 2, there are 2 pages of graphing problems. So draw a graph that models the connecting relationships of the floor plan. Use vertices to represent the rooms. 1, 2, 3, 4, 5, 6 rooms, plus the outside is the 7th room, and edges to represent the doors. So there's going to be an edge between A and B because there's a door between A and B. So there are an infinite number of possible graphs that would be correct for this problem, but I'm just going to generally just write the vertices about in the same area that they appeared in the diagram. So those are the 7 rooms. And if I count up the doors, there are 1, 2, 3, 4, 5, 6, 7 doors. Since there are 7 doors, there are going to be 7 edges. There's a door between A and B. There's a door between B and G. There's a door between B and C. A door between C and F. A door between E and F. A door between E and the outside, but the outside is G. So from E to G. All right, so for that one, I have to go maybe all the way around this way. All right, there's a door between B and E. There's a door between A and D. 1, 2, 3, 4, 5, 6, 7, 8, and one between D and E. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 doors, I guess, is what we have. So 9 edges. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, got all 9. So this is just one picture that you could draw. Now, the nice thing would be to realize that all of the vertices are even. Degree 2 here, degree 2 here, degree 4, degree 2, degree 4, degree 2, degree 2. So they're all even, which means you have an Euler circuit. And if you draw the Euler circuit here, that will then map back here and will tell you how to go through all the doors without going through another door, one of the doors twice. So if you just start at A and you go to D and then to E, and then maybe we'll come over here to G and then back down to B, and then maybe over here to C, and then down to F, and then over to E, and then the only way back to A would be to go up to B, and then finally the 9th edge is over to A. All right, so we started at A and we ended at A. And if you just go through the doors from A to D, you start here, you go into D, and then over to E, and then outside to G, and then in the door over here to B, and then from B to C, and then from C down to F, and then F over to E, and then E up to B, and then B back in. So here's the path that you would take to go through every door without going through the same door twice. And I think that's what part B is looking for. Is it possible for someone to walk through every door without entering any door twice? This is the Euler circuit problem. And the answer is yes, because all of the vertices have even degree. Or you can actually just show the path over here. Okay, for number 7 says label the degree of each vertex next to the vertex on the graph. You've done this a lot of times even today. So count the number of edges going in, 3, 4, 3, 4. Looks like there might be some intersections in the middle of that rectangle, but there aren't, because there are no dots, there are no vertices. So we have just the 3 vertices there. And then it says, sketch an Euler path. So a path begins at one vertex and ends at another. What you need to know coming into this problem is that in order for this to happen, you have to start at one of the odd vertices and end at the other one. And since it's an Euler path, it must traverse every edge. No backtracking. All right, so I'll start at A and end at C. You might want to do the first one on kind of scrap paper in case you make a mistake, because it's very easy to go down the wrong one. But all right, so 1, 2, 3, 4, 5, 6, 7, 8, and then finally end at C, and there's 9. So there must be 9 edges in this one as well. There are many other answers to this. Just make sure, notice that I've covered every edge. That's a characteristic of an Euler graph. You have to traverse every edge. You can revisit vertices. You just can't revisit edges in an Euler graph. So you can describe it this way, or you can describe it by referring to the manner in which you traverse the edges. So A, D, B, E, A, B, C, E, D, and then finally C. So one of these two approaches will tell me the path that you took. Number 8, nearest neighbor method, starting at B. So because we're telling it where to start, there will be just one exact answer to this. So everybody should get the same answer to this if you use the nearest neighbor. It's not always going to be the case, because if you're looking for the nearest neighbor, say, and then you have 2 neighbors that are 100 miles away, you can randomly select which one you go to, and that will influence the weight of your graph. So, starting at B, our choices are 210, 345, 170, or 307. And so the first thing is to come down here, and then we go B. We're also going to be asked probably the weight of this path. No, oh, there it is. What is the total weight? So I'm going to write down the 170. Once we're at D, our choices are, for the nearest neighbor, 325 to C, 310 to E, or 205 to A. Since 205 is the smallest of those 3 numbers, it is the nearest neighbor. So from D, we go back up to A, and it's 205. All right, so we've already been to B, we've already been to D. B is the last place we're going to go, because a traveling salesperson problem is a circuit. They're going to start at home, they're going to make all their deliveries or all their sales pitches, and then they're going to end up back at home. So A, our choices are to go down to C or to E. And between those 2 choices, 505 and 190, 190 is the nearest neighbor. So we're going to add 190. And then we visited all except E. And so once we get down to the last couple of vertices, we have only one choice. So we're going to go to E, and that's 365. And since the traveling salesperson problem involves a circuit, since we started at B, we have to end at B. So we have to come back this way, and we have to add that last weight. Okay, so if you add up all of those, that would be the weight we're talking about. Interesting that we formed a star, and that's not always going to happen, of course. 170 plus 205 plus 190 plus 365 plus 345. So we should all get this, because there was never a choice where we had to choose the nearest neighbor. Okay, this is a complete graph. Every vertex goes to every other vertex. How many Hamilton circuits are there? Well, I guess you have to remember this result. The number of Hamilton circuits would be n minus 1 factorial, where n equals the number of vertices. 1, 2, 3, 4, 5. Since we have 5 vertices in this picture, there are 5 minus 1 factorial, 4 factorial, 4 times 3 times 2 times 1. 24 different Hamilton circuits. Okay, and the last one is the one, okay, so it does mention Kruskal's algorithm. So what we're looking for in Kruskal's algorithm is a minimum spanning tree. So you guys just did this one in that last problem on project 7. So I'll just replicate what you did. You identify the edge with the smallest weight, because you're looking for a minimum spanning tree, because you're going to lay cable or something else. Highway distances. You're going to lay out a cable system. So you want to choose the minimum tree because you need to connect all these cities, but there's no need to have any circuits. There's no need to have a cable going from city E to city B and then another one coming from B back to E. Or if you're going from F to B and you go through E, there's no need to put a cable in here. All right, so what's the smallest? 360? Now I'm not going to write a path this time because a tree is not a path. So I'm going to indicate what's in my tree just by drawing these edges on here. and then I'll go count them up later. Is there a 400? Here's a 450. All right, so 450. And I don't think there's any more 400s. But for 500s, it looks like we've got 500, 500, 500. So just choose one of them. There's a 500. And then randomly choose another one. I guess we can do this one. 500. Still, the smallest number is 500. So let's choose the third 500. Again, we're choosing the smallest number. If you have a choice, you can randomly select the one you want. But we were able to select all three because by selecting all three, we still don't have a circuit. Okay, now that we got a bunch of disconnected pieces here, we have to have all these pieces connected. So above 500, we have 610. Cycle yet. We still have this edge here that's disconnected from the rest of the graph. So after 610 comes 630. Okay, now I can't add 630 here because if I do so, then I create this circuit. And I don't want that. So I'm going to skip 630. Go on to the next smallest number. Oh, I guess that wasn't the next smallest one, was it? 620 was. So 620. Then we would skip 630. Okay, so one more, I think, is all we need. Remember the property about trees, that the number of edges is one less than the number of vertices. So if we have 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices, we'll have 8 edges. And right now we have 1, 2, 3, 4, 5, 6, 7. So one more edge will connect these two disconnected pieces together. After 620 and 630, do we have, oh, there's a 660. But a 660 would also create a circuit here. So we can't add that to the graph. Doesn't appear to be any 700s anywhere. So then we'll move up to the 800s. And there's one. Can I add that one? And the answer is yes, I can, because it doesn't create a circuit. So here's the spanning tree. There is a path from every vertex to every other vertex. The graph is not disconnected in any way, so there wouldn't be a path from any vertex to any other vertex. There are 8 different vertices, so there are 7 different edges. And every single edge in here is a bridge. Okay, anybody add this up? Oh, thank you. Is it 4370? Kyle borrowed $8,000 from his mother to help pay for his college education. They agreed upon an interest rate of 6%. Joe paid off the loan in 8 months in one lump sum. How much did he repay his mother at that time? Okay, now it's not explicit here. But if you're going to borrow money from a relative like your mom, she probably is not going to compound interest on you, right? If she wanted to compound interest on you, then why not just increase the rate? Use simple interest. Usually in these problems, there will be reference to simple interest. So this is a simple interest problem. And so this one you cannot do with the TVM solver. So go back to the formula sheet and pick out the 2 formulas that are given to you on the formula sheet. There they are. And even all the variables will be defined. This is the payback amount. This is the borrow amount. This is the interest rate. And this is the number of years. This is the interest in dollars. Okay, so Cairo borrowed $8,000. That's the initial amount. And, you know, to keep it all straight, you know, you can say begin and then end. Begin, borrow, 8,000. Payback at the end equals the 8,000 plus whatever interest is owed. So maybe a little diagram like this will help you to decide, you know, what each of these variables might be. The interest rate is 6%. That we'll write as a decimal, 0.06. There it is. And Joe paid off the loan in 18 months. All right, now the formula is not very smart. So, you know, if you put 18 in for t, it's not going to know that what you really mean are months. You have to convert that t to a number of years. So 8 months is, if you divide that by 12, you can see the number of years. So 18 months is 1.5 years. All right, so how much does he have to repay at the end of the 18 months? Well, the appropriate formula that would work would be this one here.
I got it in the chat, Mr.
Okay, thank you. Yeah, all right, so Tasha has it in there. I'm just going to write down what she has. 8,000, 1 plus 0.06 times 1.5. And when you punch that into your calculator, you get the $8,000 plus 720 more for interest. So the interest is going to be 720, and the total payback amount would be $8,720. The $8,000 that you originally borrowed from your mother, or Kyle borrowed from his mother, and then the $720 in interest. Both have to be paid back. Okay, number 3, present value. Boy, that's PV. That's helpful. Of an annuity. An annuity is something where regular payments are made, in which semi-annual payments, so the payment is equal to $1,000. It's being made twice a year. Semi-annual, so payments per year, compounding per year would be 2. Semi-annual means twice in a year. For 8 years, T is equal to 8 at the interest rate of 8.25%. If you want the decimal, if you're going to use the formula, then you need to insert the 0.0825. But we are definitely not going to use the formula in any problem dealing with an annuity. The calculations are just too hard. So what we're going to do instead is you get out the TVM solver. N is equal to, it's not 8, but it uses 8. We got to multiply the little n value, which is twice a year, times 8, so 16. All right, the next one that comes is I%. An error that I see every now and then is students will put in this number incorrectly. What the TVM solver wants is the percent. So you want to write 8.25 here instead of 0.0825. Next comes the present value. We're going to leave that blank because the problem itself said, what is the present value? That's the thing we're looking for. The payment, all right, we're going to put in $1,000, but we're going to put a negative $1,000 because that's really cash out. Cash out, cash in will come back in later. Okay, there's going to be nothing left. So in a present value problem, the future value is 0. And then last is payments per year, compounding per year, and that's equal to 2. So remember that, you know, if you can use the TVM solver, you probably want to because it's very, very accurate. And it'll get you to the answer if you type in all the inputs correctly. And it'll do it instantly. You know that there are some of these values that you would put into the TVM solver that are easier to work with than others. Like the interest rate is almost always given to you. Okay, so 11,545.58. So when you report your answer, report it rounded to the nearest penny. Okay, continuing along. Jeff wants to buy a $1,500 computer in 12 months. How much money must he deposit at the end of each month? Okay, so they're suggesting that there's a regular deposit or a regular payment investment at the end of each month. This too is an annuity. Anytime you have an regular payments being made, either for a loan or if you're investing for yourself, it involves an annuity. So I'm just going to go ahead and write down the inputs for the TVM solver. Okay, Jeff wants to buy a, all right, so if I do the picture here, and I look at Jeff's savings, at the beginning, he has $0. And then after 12 months passes, he wants to have $1,500 so we can buy that computer. At the beginning, that's the present value, and at the end, that's the future value. So again, a little diagram like this might help you kind of place some of those values in the TVM solver. All right, so N is 12, 12 equal payments. The interest rate is 6.5. There. We start with nothing. We know that we're going to end up with $1,500 in the future. Present value is 0. Future value is 1,500. How much must he deposit at the end of each month? So there's monthly payments. So C/Y, P/Y is going to be 12 payments per year, 12 compounding periods per year, 12. And the payment is what we want to figure out. So if I just took $1,500 and I wasn't earning any interest, that would be a $125 payment. If I invest $125 for 12 months, I will have the $1,500. But if we get some interest added onto that, I won't have to invest $125. I can actually invest a little bit less than that and then count on the interest to bring me up to the $1,500 at the end. Okay, so let me type all this in. 12, 6.5, 0, 1,500, and 12. All right, so get all the numbers in there except for the one you want to calculate. Put your cursor right there at payment, and then alpha enter. So it's not $125 each month. You only need to invest $121.31. So now remember that if you just stop here, you're not going to get the last point. Most of these problems will be, 3 points. But as a reader, I still don't see the answer. Because if you want me to see the answer, then you're going to assume that I'm going to get rid of that negative sign, and then I'm going to round that to the nearest penny. And you can't rely on me to do that. So you have to take this number and write the final answer in the appropriate form. So what should that monthly payment be so he has $1,500 at the end of 1 year? There it is. No negatives, rounded to the nearest penny. Okay, still seeing nothing else in the chat. We're just going to continue on. Lisa deposits $1,500 at the end of each quarter. Well, right there, when I read that and I understand that phrase, that means that Lisa is going to make more than one payment, more than one deposit, more than one investment. $1,500 is leaving her checking account and going into some other investment thing at the end of each quarter. So 4 times a year, she's dumping $1,500. The important thing here is that there's going to be a sequence of payments made. So therefore, it's an annuity. And so we're going to get the TVM solver out and let it crunch the numbers for us. This time, the payment is $1,500. We'll put a negative in there, indicating that we're investing, so cash out of the checking account goes into the how much will be in the account. All right, so again, if this is the picture, we have the present value is 0, and the future value over here is what we're looking for. This whole time span is 20 years, and the interest rate is 9.3%. Compounded quarterly, so payments per year, compounding per year is 4. What is N again?
The number of years
Times
the quarterly, which is 4.
Yeah, times 4. So it's always the P/Y number times the number of years. So 4 times 20. So N is going to be 80 this time. Now, a lot of times we'll ask you, well, how much did Lisa invest? What was her total contribution? And then how much of what she ended up with in the future was interest that she earned over that 20-year period. So we have 80 for N, and then 9.3, and then 0, and negative 1,500. Future value is what we want to calculate, and 4 quarterly payments each year. So we know 6 of the inputs. We're always going to leave this to be end because we're working with ordinary annuities. And cursor here, alpha solve, and there it is. So let me write that number down, 341187.1961. Okay. Now, Lisa made 80 deposits of $1,500. So this is how much that Lisa contributed, $120,000. Everything else she ended up in that account, everything else that ended up in that account must have been interest. So if the problem also goes on to ask you, well, how much interest was earned? You'd say, well, this is how much she has at the end of those 80 quarterly payments or 20 years. And then if you subtract 120,000, $221,000 was interest. Okay, Chris's current salary, next one. So presently, Chris has a salary of $32,000. So this is at the beginning. Right now, Chris has this amount. This problem says, what will his salary be if he gets a 5% increase every year over the next 10 years? Well, in the future, his salary will be something more than $32,000 because he's getting a 5% increase in his salary every year. There's no mention of compounding other than the phrase per year. So that would mean once per year. So the compounding factor is just once. There's going to be no additional payment. Well, it's not even in that context, right? It's like, here's my salary today. It's going to grow with compound interest over 10 years. What is it at the end of the 10 years? We've got a 5% interest rate, 10 years. So T is 10. So if you start off after you graduate and you get a job and you're making $32,000 a year, if you get a 5% increase to your salary over a 10-year period, you can actually calculate here how much you'll make in 10 years. For the same company, just getting that cost of living increase, well, 5% is more than a cost of living increase these days. All right, for this one, and this is the rare problem that you really have a choice. You can use the TVM solver for this one, or you can use the formula. If you use the formula, it would look like this. I prefer the formula in this case, much faster. But if you use the TVM solver, these are the inputs that you would see. N would be 10, because the payments per year, compounding per year, that's equal to 1 in this case. There's no mention of quarterly compounding or weekly compounding or anything else. The future value is, what is the future salary if I get a little bit of an increase? In this one, there's no payment. There's no amount added on. Now, you could say, well, in a situation where he gets a bonus, that would be something added on, but there is no mention of that in this problem. Present value is 32. And the way the formula works, we would put a negative to that. The positive would come out in the future. And the 9% is 5. So no matter how you do it, you're going to end up with the same exact number, rounded to the same, generally the same number of decimal places. So 32,000 times 1.05 to the 10.
2124.63.
Okay, so 52124.63. Yep. And the TVM solver would give you that same number right here if you use the TVM solver. Okay, now the next problem is one that you had on one of those projects. And this is the idea where you go to the car dealership and they have different financing options for you. And your goal when you see these options is that you want to pay the least amount for the car. And if you can afford the payment, you don't really care if you pay the card off in 3 months, not 3 months, 3 years, or 7 years. You might want to have it paid off sooner, but in this problem, we're looking at your general financial well-being, and we want to pay the least for the car over any period. Okay, so Hannah is offered two options when purchasing a $23,000 car. Option one offers 6.99% financing for 5 years and $2,500 cash back. So what that means is that the car was originally this amount, and let's just say that it's after taxes and everything, but then they give you this cash back. So instead of borrowing $23,000, since we get this rebate or this cash back, we're going to subtract. They don't actually give you a check for $2,500. They just use it to pay down the selling price of the car. So the present value here is going to be $20,500. So it's the 23,000 minus the 2,500. And the little n is equal to 12 because we pay monthly payments. In the TVM solver, this would be payments per year, compounding per year would be 12. Okay, option two. Option two, the loan amount is 23,000, but there's no cash back on this option. But the interest rate is a little lower. It's 5.99%. And the loan only goes for 4 years instead of the 5. Again, the little n is 12. Okay, so the setup of the problem is what takes all the time. And so this is an annuity because you're going to be making regular payments for your car, monthly payments, same monthly payment for either 5 years or 4 years. And it says determine the monthly payment for each of the two options and then decide which option is best if your goal is to pay the least amount for the car. Okay, so let's do option one first. Both of these require use of the TVM solver. So in the first option, 12 months, and we have 5 years. So over 5 years, if you make a monthly payment every month for 5 years, that's 60 payments. So n is always the number of payments. Not the number of payments per year, the number of payments total. I%, because we take it out for a longer period of time, we have a higher interest rate. The present value is the present value of the loan. Remember, it was originally $23,000, but then we had a rebate, $2,500, took the loan value down to $20,500. The payment is what you're after here, so we're going to leave that blank. And at the end of those 60 payments, the future value of the loan would be 0. Payments per year, compounding per year. For cars, generally, it's monthly payments. For option two, and now for this one, we have monthly payments as well, but we're only paying on this loan for 4 years. So we're going to make 48 total payments over a 4-year period. The interest rate is a little bit lower with option two, 5.99 instead of 6.99. The present value of the loan is $23,000 because we didn't get any rebates. No cash back. All right, the payment again is what we want here. Keep in mind, we're only going to make this payment for 48 months instead of 60 months. Like the other problem at the end, the value of the loan will be 0. And then payments per year, compounding per year will be 12. So the first problem says just, calculate the payment for each of the options. So we're going to rely on the TVM solver to crunch the numbers for us here. All right, so we have 60 and 6.99 and 20500. Going to calculate the payment. Future value is 0, monthly payments. All right, so this is what you want in the TVM solver, leaving blank what you're trying to calculate here, which is the payment. All right, so there it is, and I'm going to round it to the nearest penny there. 405.83, option 1. And the other one, we have 48 months instead of 60 months, a lower interest rate, 1% lower, but no cash back. Everything else is the same. So over here, there are $540.05. So if you're going to take longer to pay off the loan, your payment is going to be a little lower. And also, we have a little bit of cash back, so the present values are not the same. Okay, now Hannah's goal is to pay the minimum amount for this car over the life of the loan. Which one should she choose? All right, so here's how the reasoning goes there. So for option 1, total payments. All right, for option 1, she paid $405.83 and made that payment 60 times. So this is the total amount that she's paid. And remember, this was an original $23,000 car. All right, so option 1, total paid would be $24,349.80. That's option 1. And option 2, the total payments. All right, so the payment was $540.05 for option 2, but we were only making that payment 48 months instead of the 60 months. So we need to multiply this by 48, and then that would be the total payments. 540.05 times 48, and that's 25,922.40. Okay, so it says explain why using specific numbers. So one way to do that would be to just calculate the total amount paid and then choose the smaller of the two, because the goal is to pay the least amount of money. So clearly this is the best option for a couple of reasons. First of all, you can see it's she would be paying less with option 1 than with option 2. Secondly, the monthly payments are a little bit lower, $405.83 versus $540. So option 1 is clearly the better option. The only downside would be that with option 1, she has to pay a full 5 years worth of payments, whereas in option 2, she has to pay only 4 years. So she's going to pay off the car sooner with option 2 than with option 1. But other than that, option 1 is the best. So, well, we have about 11 minutes left. Do you have a preference as to the Johnny on the spot investing for the future versus the home mortgage problem? Any preference? Because we're not going to be able to do them both. Betty and Preston took out a 15-year mortgage for $195,000. In loan language, this $195,000 is the present value of the loan. And then the interest rate is 7.5%. Compounded monthly and equals 12. This occurred in 1995, and then 5 years after paying off the original loan, they decided to refinance because the interest rates had dropped. So they paid 5 years on the original mortgage, and that means that there were 10 years remaining on the original mortgage, so they decided just to take out a new 10-year mortgage on what was left, on what they owed. But they refinanced because the interest rate lowered from 7.5% down to 6.5%. What was the original mortgage payment? Okay, so this is kind of a standard annuity problem. We have monthly payments for 15 years. So that would be a total of 180 payments that Betty and Preston would have to make if they went with the same loan. The I%, we're talking about the original loan now. So this was 7.5%. The present value of the loan they gave to us to be $195,000. The payment is what we're interested in here. What was the original monthly mortgage payment is what it asks. At the end of that 15 years, the future value of the loan would be 0. And then payments per year, compounding per year is 12 because we need to make monthly payments. All right, it's an annuity, so definitely use the TVM solver here. We have 180 on N, 7.5 on the interest, 195,000 on the present value. Payment is what we're going to calculate. Future value will be 0, payments per year, compounding per year, 12. So we're doing alpha solve on that. And the mortgage payment is $1,807.67. So be sure to write that final answer off to the side in context, the appropriate punctuation. Now, the reason this problem is so important is because if the interest rates go down, they can live in the same house but dramatically decrease their payment. You know, if you mean dramatically, would be like, you know, $100 or $75, but it's something. And if they'll actually save themselves some money in the long run, then why not do it? Okay, what was the balance of the original loan after the first 5 years? So when they ask for the balance of the loan, what they're asking for is the present value. What is the present value of the loan? That is, if I had to pay off the loan today, what would I have to pay? Now, everything else in this problem is based on the original loan. So N we have to figure out because N has changed because we no longer have 180 payments. After 5 years, we've already paid 60 monthly payments. So we start with 180 payments and we subtract out the 60 that we've made. We still have on this loan 120 payments remaining. So you can think of N in these refinancing problems or any time. N is the number of payments remaining. So after 5 years, 60 payments made, 120 payments remaining. Now the interest rate, I'm not going to change to that lower rate yet, because the first thing I have to do is to figure out what the present value on the current loan with the current 7.5% interest rate. So this remains as 7.5. The payment is the same payment that we just calculated, and be sure that you leave it in there as a negative. The present value is what we're trying to calculate. Future value 0, as before. Payments per year, compounding per year, none of these will change. So as we go from the first use of the TVM solver to the next use, the only number that we're changing here is the N. We change one number, the 180 to 120, and then we come down and recalculate the present value. So after 5 years of making $1,800 payments, we still owe $152,000. Okay, now the next one is, okay, now that this is what we owe, so what we want to do is we want to pay this off and start a new loan. And, you know, there's no mention of closing costs or anything here. So we're just going to refinance this new amount. And we're going to refinance it, it says up here, into a new 10-year mortgage. So we have 10 years of monthly payments, so we're just going to continue with 120 payments. Here is where we change the interest rate, because we're looking for the payment on the new monthly payment with the lower interest rate. So here's where we change this 7.5 down to 6.5. The present value is the present value that we calculated. We're just going to pay this one off and start a new one. 152. This is not money coming out of your pocket, so therefore we're not going to put a negative in front of it. The new payment is what we're going to try to calculate here. And then the future value in the new loan after 10 years will be 0. Payments per year, compounding per year. We ended one mortgage that had monthly payments, and we're starting a new one with monthly payments. So from what we last did, all we have to do is come up, change the interest rate to the lower interest rate, and then go down and calculate the new monthly payment. So other than just changing one number and then calculating something else, so we have a new payment of $17.29. And you can see that the payment did go down. It didn't quite go down $100, and that's because we have only a 10-year mortgage. If we had a longer mortgage, this number would have come down a lot more. But still, we're saving about, what is that? $80, $78 a month. So 78 times 120, that's a fairly significant savings. $9,000 savings, $9,300, just by refinancing. Okay, so this next question asks, if the closing costs are $2,000, we can look at our savings this way. If we take the original payment and subtract the new payment, the amount that we're saving each month would be this amount. So let me just go ahead and calculate this, $78.48. So if we're going to save that amount per month, if we take the $2,000 and divide by that $78.48, this would tell us how many months it would take us to recoup our closing costs. 25.5. That's about 2 years. So remember, our new mortgage is 10 years, but after just over 2 years, we will have, just in savings from our monthly payment, we would make back that $2,000 that it costs us to refinance the loan.